In this video, we're going to be covering section 5.3, which is going to cover how to graph sine and cosine. And I suppose not just sine and cosine, but also transformations of their graphs. So, is what I want us to do is actually start off by kind of just filling out this table here. So, we have these values of theta, which are our inputs. You can kind of think about these as our x values. And then over here are outputs, sine of whatever the corresponding angle is. And so, for instance, you might remember sine of 0 is 0. Okay. Sine of pi over 6 is 1/2. Sine of pi over 4 is going to be root 2 over 2. Let me zoom in here a little bit. There we go. Pi over 3, or specifically sine of pi over 3, that's going to be the square root of 3 over 2. And I might use a slightly smaller marker here so I can write these in a little bit neater. Let's try that. And then sine of pi over 2 is 1. Okay. So these were all the first quadrant angles, and now we're on to the second quadrant. Okay. And if you don't remember these, of course, you can go to your unit circle. So for instance, we could come over here and look at sine of 2 pi over 3. And so sine should be the y value here, right? So that's the square root of 3 over 2. So we'll go ahead and we'll fill that in here. And the next one should be the square root of 2 over 2. And then lastly here, sine of 5 pi over 6 will be 1/2. And actually, I'm going to do one more here before we start doing some of our graphing. Sine of pi, this is 0. Okay. All right, so I just want us to graph these here first, and then we'll talk about kind of graphing the rest of this. And is what we're going to see is it's going to end up the only really important points are actually going to be spaced out by pi over 2. So for instance, this will end up being one of our important ones. This will end up being another important one. And sine of pi will be another important one. But you can see these three that I have here in the green at the moment are just zeros and ones, and the rest of these are the numbers that aren't so nice. All right. Well, let's go ahead and set up the x-axis here before we actually plot these points. So I kind of mentioned that these three that I have in the green here so far are going to be the important ones. So it's going to end up that when we go to graph this, we'll have our pi over 2 here. Adjust my spacing here a little bit. There we go. Pi over 2. And then pi. If we add another pi over 2, that's going to be 3 pi over 2. And then if we add another pi over 2 to that, that's going to be 2 pi. There we go. Add another pi over 2, that's going to be 5 pi over 2. Add another pi over 2. We get, 6 pi over 2, which is going to be 3 pi. And another one, we'll have 7 pi over 2. And I'll probably end it after the 7 pi over 2. So a single more pi over 2 will get us to 4 pi. There we go. All right, so again, let's go ahead and focus in on the values that we have up here now. Notice that so far they only are in between 0 and 1. So I only need to go up to 1 here. Let's maybe make 1 maybe be right here. We could have maybe a half be here. This square root of 2 over 2, let's see approximately what that one's equal to. So square root of 2 over 2. Yeah. And while we're at it, let's also find the square root of 3 over 2. Those were the other two kind of values that were popping up. So we have about zero point 0.7 and about 0.85 roughly. Okay. So let's try to find where we think maybe zero point 0.7 would be. Say somewhere in here. And then that 0.86 or so is probably somewhere in there. So just eyeballing this does not have to be perfect. Okay. So that first one was, first point here is 0 comma 0. So it's right here. All right. And then the next one that we have is at pi over 6. So pi over 6 is actually a third of pi over 2. Okay. So I want to be somewhere in here. Okay. Approximately there. But I want my y value to be, what, a half here. There we go. And then if we were to look at pi over 4, that should be directly in the middle of 0 and pi over 2. So somewhere right in here. And so if I go up to my y value here, the square root of 2 over 2, which was about 0.7, I'll put it somewhere in here. Right. And then after that, we have pi over 3. And pi over 3, let's figure out what fraction pi over 3 is of pi over 2. Okay. So we have our pi over 2. And so we want to know what fraction pi over 3 is of this. Okay. Okay. So I'm going to take pi over 3 and I'm going to divide it by that pi over 2. There we go. So I should go about 2/3 of the way now to get that number that I'm looking for here. So 2/3 of the way, that's probably somewhere right in here. There we go. So if we go to put that up here, we should be now up to the square root of 3 over 2. So probably somewhere right in here. And then lastly, at pi over 2, it should be up to 1. And then if I fill in the next 3, I'm going to do these a little bit faster. It should be kind of symmetric here about this pi over 2. So I know approximately what this should look like. There we go. And then sine of pi, that's going to be 0. So these are all these points plotted. It should look a little more curved than I have it looking. But let's go ahead and kind of connect the dots here. So this should look something like, let's see if I can give this a little bit more curvature. Okay, something like that. Okay. And I'm going to actually remove those orange points here in a minute. But is what I want you all to see is that we get this kind of almost parabolic looking piece here. Okay. And if we were to keep going with this, is what we're going to see. I'm going to put down here a -1. We're going to see that as we go from pi to the next x value I've chosen here, 3 pi over 2, that we're going to go actually to the bottom of the wave. Okay. And you can kind of see going from our first x value to our second one here, we go from the middle of the wave to the top of the wave. And when we went from this specific x value here to the next one, we went from the top of the wave to the middle of the wave. Okay. And so now we're going to, again, go from the middle to the bottom. Okay. And it should have some curvature to it here. And then we should go back up to the middle of the wave. Okay. We're literally just making a wave pattern here. And then at the next spot, let's see, we're going to be back up to the top. And so you can kind of fill these in really quickly once you know the pattern that this is going to follow. But again, I'm at the middle of the wave, to the top, top to the middle, middle to the bottom, bottom to the middle. And it's just going to keep repeating this process over and over and over again here. And so, again, I didn't plot these points here perfectly, so it doesn't look as curved as it probably should. If I were to maybe try to make this look a little bit neater now, probably just go something like this. There we go. Right. And if we want to, we actually can fill in these values on this table, even though we didn't use them actually to make the rest of the graph here. We could have though, but so 3 pi over 2. Well, sine of 3 pi over 2, we should be at the bottom of the unit circle, meaning that if we were to look at what sine would be, it should be -1. Okay? And if we actually come over here to look at our graph, we'll see, oh yeah, it's -1. Sine of 2 pi. So we've made one complete revolution. So we should be back to a y value of 0. And you can see sine of 2 pi is 0. And this pattern will just continue. Okay. So again, we were at the bottom of the wave, the middle. We should go back up to the top, and then the middle, and then the bottom. Okay. And again, if we check sine of 7 pi over 2, we have here, it's just -1. Okay. So this is repeating this nice little pattern here. And when I go to think about the parent function for sine, I specifically think about this section here as the parent function. And the reason I'm talking about a specific section here is we only need to know a little bit of the graph because it's going to just continue to repeat the pattern. Okay. And so one of the things I tell myself is that sine starts at the middle of the wave. You can kind of see here when x is 0, sine is 0, or when theta is 0, sine is 0. So I just always make that note. And so really what I mean here is just plain old y equals sine of theta, um, with no transformations done to it. At x equals 0 or theta equals 0, sine will be 0, which is the center of the wave. All right. So let's go down here and take a look at cosine as well. Is what's going to end up happening is it's going to look very similar. And you can see here, even though in the beginning we plotted some extra points so we can get an idea of what the shape would look like, in the end, we only really needed to find the sine at multiples of pi over 2. Okay. So I'm going to come back over here. And again, you're seeing a bunch of angles that are multiples of pi over 2. Okay. And so cosine of 0 is 1. Cosine of pi over 2 is 0. Cosine of pi is -1. Okay. And this same exact pattern kind of repeats itself. This is going to be the top of the wave. This is the middle of the wave, the bottom. Okay. When I go to graph, of course. Okay. Then back up to the middle, then to the top, the middle, back down to the bottom, and then the middle, okay, and so on. Okay. And so we can go ahead and we'll go ahead and graph these x values. I'm going to go out to 2 pi on this one here as well. So we have 7 pi over 2, and then finally an 8 pi over 2, which is 4 pi. There we go. And we just need to go up to 1 and down to -1. And let's go ahead and plot all these values here. So again, cosine is going to start at the top of the wave, unlike sine, where sine starts at the middle of the wave. And so since we're starting at the top here, we're going to go down and then back up to the middle, back to the top, so on here. And then I'm just going to connect this with a smooth curve. And it's just going to look like um, a bunch of waves, just like the sine function did. It just, again, it starts at a different location. And when I think about the parent function here, I'm always thinking about this right here. Okay. Notice for both of these, I'm thinking about 0 to 2 pi, and that's because the period of these functions is 0 to 2 pi. If I can remember what it looks like on 0 to 2 pi, then I can just keep continuing that pattern. And so when I go to think about that as my parent function, again, this means I'm thinking about cosine starting at the top of the wave. All right. So now that we know essentially what the parent functions look like for sine and cosine, we're going to want to go through and perform transformations on these. So let's go ahead and scroll down. So when it comes to graphing sine and cosine, I like to always think about them as being set up like this. Okay. Or I guess I could also include the one for cosine here. Okay. But as what you'll notice is up front on each one of these, we have some constant. Okay. And you might remember when you multiply a function by a constant, it's either going to cause a vertical stretch or a vertical compression. Okay. If the number is bigger than 1, it's going to cause it to stretch. So the y values, or let's say a is equal to 2, now the y values are going to be twice as big. Okay. Now, we don't uh, we talk about something very similar here for A. We call it the amplitude. And we actually take the absolute value of A to find what we'll call the amplitude. But I do want us to just note here that A itself, again, is going to be our vertical stretch or vertical compression. So this works just like it worked when you were taking pre-calculus 1. And so that's what we're going to kind of see with all of these here. So the next one I have here is this 2 pi over b. Okay. So this is actually what we're going to call the period. Okay. But I want us to know why this is the period here. But let me use a little bit bigger marker here. There we go. So this b right here, you can see it's in front of the x. Okay. So this b here is always either going to cause a vertical, or sorry, not vertical this time, horizontal It's going to cause a horizontal stretch or a horizontal compression. Okay. But you might remember this works the opposite way that you would think. If B were equal to 2, we'd actually have a compression, okay, a horizontal compression. Versus if B were, say, equal to 1/2, we'd have a horizontal stretch. Okay. And so, is what's going on here is, again, if, say, B is 2, we're having a compression. So we're going to complete one period faster now. Rather than completing it in 2 pi units, we'll complete it in 2 pi over B units. Okay. So again, while this does give us our period, the note here would be that B causes a horizontal stretch or compression. And that's why, again, it's affecting the period. There we go. And then a little bit easier one here next. We have this plus D. So this also works just like when you originally learned about transformations. This is going to scoot us up or down. So if D is positive, it'll scoot us up. If D is negative, it'll scoot us down. So I'm just going to write this in here as a vertical translation. Right. And then we have one more here. We have C. Okay. But I do want you to notice how these are factored. Like this B has been factored from what we have here, or it's outside of that x minus C. Okay. So that being said, this C is going to be our horizontal shift. Okay. So if C is, say, a positive number, let's be a little bit more specific here. Let's say that right there it says x minus 5. So that's going to scoot us to the right 5 units, versus if it was x plus 5, it would scoot us to the left 5 units. Okay. Now, we do have a different name for this here. We're going to call this instead the phase shift. So let's go ahead and scoot down and we'll write that down here. So C is equal to our phase shift, which is really just another name here for our horizontal translation. All right, and then we have one last thing that's not quite so clear. Um, I want to make a note here. So, like these x values that we're looking at here, these are oftentimes called quarter points. Okay? And in fact, if you were to take the period of sine or cosine, which is 2 pi, and divide it by 4, so splitting it into a quarter, you'll get pi over 2. Okay? And notice that is what we spaced by. Okay? So it ends up that your quarter points are the points where sine and cosine are at 1, 0, or minus 1, meaning these are the easy points to plot. Okay? So when it comes down to our spacing down here, all I'm really talking about is take that period and divide it by 4. So let's go ahead and again, we'll write that in here. Let's go like this. So it's just the period over 4. Okay. So these are all the things I want you to calculate each time you graph sine or cosine. And as you are working your way through the online homework, if you're not as familiar with graphing sine and cosine, I highly recommend um, graphing as many of those as you have time for by hand. So example 1 here. So this one, we can see it has a various number of transformations here. One thing I'm seeing is this 3 and this 1 here. So I know that my amplitude, which I'm going to think about here as being very close to the same thing as my vertical stretch, my amplitude is 1, or A is equal to 1. What else do we have here? We have that vertical shift that we were. Oh, I wrote 1. Our amplitude's 3, isn't it? It's this number right here. But my vertical shift, this plus 1, I can write that in here. Right. So with these two values right here, we can actually set up our y-axis. Okay. So your amplitude is actually really how far we're going to travel from the middle of the wave to the top of the wave, or similarly from the middle of the wave to the bottom of the wave. So up here, when we're talking about the parent function for sine and cosine, the biggest and the smallest that they can get is 1 and minus 1. But if we were to say multiply this cosine function by 3, now it's going to go up to 3 and down to minus 3. Okay. So again, that's how far we would go, though, from the center of the wave is that amplitude. Okay. And maybe we'll add that here, that's what the amplitude's really telling us. I'm going to say distance. There's the idea. And when I'm talking about distance here, I mean the vertical distance. Right. So when I go to set this up, I need to, for one, keep in mind that I'm going to have been shifted up 1 unit. And then when I say shifted up 1 unit, that's how far we're going to shift up the center of the wave. Okay. And then we'll want to go up 3 units from there to get to the top. So here's what I'm trying to say is that when I go to label this, I'm going to have my 1, 2, 3, 4. I want to make sure that I can at least go up to 4. But you know what? Let's make sure we have as much space as possible here. I'm going to call this up here 4. And let's see if we can mark in the rest of these pretty evenly. So we'll call that 2, 3, and then a 1. There we go. And maybe I'll just try and do the same thing down here. Although we're not going to need all these. I just want to keep the spacing even here. There we go. So yeah, this will be the center of our wave, 1, y equals 1. We'll go up 3 units because our amplitude was 3. And similarly, we'll go down 3 units. So down 3 would be to here. So down to minus 2. There we go. So we've set up our y-axis. Let's go ahead and compute a couple more of these things. So B up above was the number in front of the x. And is what you'll notice here is, for one, we don't have x's, we have t's, but there's nothing in front of this t. Okay. So our b here is actually a 1, which implies that the period is unaffected. The period is going to be equal to 2 pi over b. So this is 2 pi. This also means that the spacing will be the same as the spacing we've seen all along so far. The spacing here should be the period over 4. And so this is going to be pi over 2. But there is one more thing that's going to happen horizontally here. it looks like we have a horizontal shift. Okay. So let's go ahead and include that here as well. So our phase shift is what we're going to call it, but again, that's all it is a horizontal shift. So your phase shift is just this C value here, pi over 3. And again, we can go up and look at that again. Um, so right, this was C. Some number that we're going to be adding or subtracting with X. So is what I want us to do here is actually start off on the X-axis by graphing the phase shift. Okay. And so our phase shift here is pi over 3. So let's go ahead and do that. So let's maybe call this right here pi over 3. Okay, there we go. Now is what we want to do from here is we would like to add the spacing to this. So for instance, if I want to do this quickly, I could just take my 1/3 instead of pi over 3. I'm leaving out the pi. And I could add, and instead of adding pi over 2, I'll just add 1/2. And I could hit math frac. And so there is our next point that we'll want to plot on the x-axis. But again, we could add another half to that. Okay, and hit math frac. And so we could get all those numbers that go on the x-axis here pretty fast. But I also want to note that the number pi over 3 is a certain fraction of pi over 2. So if I want to keep this looking consistent, it might be nice to know maybe how these two numbers compare. Let's maybe actually plug in pi over 3 into the calculator so we can see it. So there it is. And we want to know what fraction this is of pi over 2. Try that again. Okay. So it's about 2/3 the size. Okay. So is what I'm getting at here is when I go to add pi to this, I need to go a little bit further than the distance we had from here to here. I want to add about an extra third to it. So let's say we think that that looks maybe like something like that. I think that looks about right. So we said that the next one would be 5 pi over 6, I believe. It's up here. Yeah, 5 pi over 6 and then 4 pi over 3. Let me double check that, but I'm pretty sure it was 4. Yeah, 4 pi over 3. And so then we could take our 4/3 and add an extra 1/2 to it here. And let me clear some of this out and scoot down here. There we go. So you have 4/3. We could add our 1/2 to that. Hit math frac. So we have 11 pi over 6 now. And if we add another 1/2, let's do that. We can hit math frac again. There we go. So we get 7 pi over 3. All right, and we should be noticing maybe a little bit of a pattern here if we wanted to plot a lot more points. Like these right here are exactly what, just pi units apart. And same with these ones. These ones are just pi units apart. Um, so in other words, I know that the next one here, I'm going to, let's see, add a 6 pi over 6 to that. So it's going to be a 17 pi over 6. Right? I added 6 pi over 6 to get from here to here, and another 6 pi over 6 to get from here to here. Similarly, to go from here to here, I added a 3 pi over 3. So if I add another 3 pi over 3, I'll get a 10 pi over 3. I'm going to make this a little bit smaller. There we go. All right, so we can probably get the graph done from here. Okay. So is what I want you all to remember here at the moment is we're working with sine here, and sine starts at the middle of the wave. Okay. Now the middle of the wave for us has been scooted up 1 unit. So the middle of the wave now is technically right along here. But also, sine again starts at the middle of the wave, but we've been scooted over to the right pi over 3 units. So I want to come over here, and at pi over 3, that's where I want to start off at. Okay. Now, sine from the middle of the wave, you might remember, you might not remember, but it either must go up or down. And we do need to remember which one of those two it does. So if we come back up here to the parent function, is what you'll see is sine starts at the middle of the wave and then goes upward. So I'm going to do just that. I'm going to go over to 5 pi over 6, my next quarter point, and now I should be to the top of the wave. Okay. And then from there to at our next quarter point, we should be to the middle of the wave. Okay. And this dotted line I have here in the pink, you do not need to make that. I've just done that to make it clear that that's where the center of the wave is now. Okay. And then at our next quarter point, we should be now down to the bottom of the wave, so 3 units down from the middle. Okay. Next quarter point, we should be back up to the middle. Next quarter point, that puts us at the top. And then this last one here at the middle. Now, let's go ahead and connect the points, and then maybe we can extend this graph off to the left here a little bit. Okay. So I'm just going to make this look smooth, or try to. Here we go. Now, let's say again we did want to extend in this direction a little bit. Well, we were adding pi over 2 to move to the right. Now we'd want to subtract by pi over 2. So if you actually subtract the pi over 2 from this, I believe we're actually going to get minus pi over 6. And that's going to land us about right here. So right, pi over 6 should be half the length of pi over 3. But we can also verify this. So right, we have our 1/3 minus 1/2. Okay, and then math frac. So we get, yeah, minus pi over 6. So we got it here. The next one, right? You might remember we had a little shortcut we were doing, right? We were adding 3 pi over 3. Well, if we subtract 3 pi over 3, we'll get a minus 2 pi over 3. That put us somewhere about right here. And maybe we could add in a couple more points. So we were at the middle of the wave here. So then if we scoot over our quarter point, we should be to the bottom of the wave now. So here, and then the next quarter point back up to the middle, which is not there. It is right here. There we go. Now, if you are ever asked to graph a certain number of periods, I usually do look for a couple things. One is I know, for instance, like the parent function of sine or cosine. Okay. I might think about for sine maybe something like this. Okay. So I would want to make sure that I completed two of that shape. Okay. But also, you could just use the fact that you have the period already calculated here and just make sure you graph twice that distance if you were asked to say graph at least two periods. And so, for instance, here so far, um, I think we have exactly two periods. But one way we could again check is we could see, well, how far did we graph? So we went from minus 2 pi over 3 up to 10 pi over 3. So let's go ahead and figure out what that distance is. I'm going to compute that right here. So we have 10 pi over 3 from 0 to the right. And then from 0 to the left, we have from 0 to 2 pi over 3, or 2 pi over 3 units in distance. So this is 12 pi over 3, which is 4 pi, which is double the period for this function. Okay. So we've actually graphed, again, precisely two periods here. Right. The way that I am seeing this visually, though, right now, is I see this is one period, and then I'm looking at this spot here as the second period. Okay. So one way to think about a period is it would have kind of one of these downward facing shapes and one of the upward facing ones combined to complete one period. So a lot of ways to think about this. All right, let's go check out the next one. Okay. So this one's going to be a little bit tougher. I'm seeing a few things here that are going to make it more challenging. So one is this time we do have a number in front of the x, but you might remember that the two forms I had listed up above here, you need to factor that number out. Okay. So let me show you all what that would look like here. So if we were to factor that 3 out, let's see what this turns into. We get a minus 2 cosine. And so I'll pull out that 3. And then that leaves us with x plus some question mark here, which we'll figure out in a moment, and then minus 1. Okay. So there's more than one way to do this. Okay. You could kind of play a little bit of guess and check, but remember when you do factor something out, to test whether you've done it right, you could kind of distribute the 3 back through via multiplication. Okay. So in other words, factoring it out, um, instead of distributing through, if distributing through is multiplication, then factoring out, you could think about kind of using division. Okay. And so here's what I mean is if I were to take pi over 2 and divide it by 3, okay, I could think about that 3 down there as a 3 over 1, and then we could flip and multiply. And so that actually gives us pi over 6. There we go. So that pi over 6, that's what I'm going to write in place of this question mark. Okay. And do check after you factor. If we distribute back through, do we end up with what we started? Okay. And so yeah, we'll get 3x and we'll get 3 times pi over 6, which will indeed simplify to pi over 2. So we have this written in the way we need now. Now we need to just go ahead and write down all of the transformations. So for one, again, our amplitude is actually the absolute value of A. So when I go to write my amplitude here, I'm actually just going to say A is equal to 2, or my amplitude is equal to 2. But because there is this negative here, this is going to cause a vertical reflection, is what I like to call it. Um, there we go. And also, we have this -1 down here, so that's going to give us a vertical translation down 1 unit. Or if you just want to call it vertical shift, that's perfectly fine too. I want to say -1, just signifying down 1 there. So this again does allow us to actually set up the y-axis. So this is going to scoot the center of the wave down 1 unit, and then we'll go up and down 1 unit from that new center. So let's see. If we go down 2 units from -1, that would put us at -3. So let's maybe divide this into thirds, each the positive y-axis and the positive x-axis. So, or try to. So I'm going to call that 3 here. And then similarly down this direction. And again, our center of our wave is at -1. If you like to put it in here, a dotted line, you're more than welcome to. Maybe I'll put it in yellow this time so it doesn't stand out too much. Can just help you keep track of where the center of the wave is. Oh. So that's set up. Now we want to start thinking about the horizontal um, shifts and compressions and potentially stretches. So this is what we call B, this number here that's in front of the X, and that's going to cause a vertical, or not a vertical, a horizontal compression. So rather than the period taking 2 pi units, it's going to do that in a third of the time now. It's going to be 2 pi over 3 now is going to be the period. So let's go ahead and fill that in. So 2 pi over b. That's how we'll compute that period. We also are going to want the spacing here now. So the spacing should be the period over 4. So if we start simplifying, that's going to give us 2 pi over 12, which is going to be pi over 6. All right. And additionally, we have something else that's going to involve pi over 6. So this is our horizontal shift, but notice there's a plus sign here this time. So this shift is going to be to the left. And that horizontal shift we call here the phase shift. Okay. And I'm going to just write it in as minus pi over 6. The negative is indicating to us that we're going to move to the left. Or not move to the left, but shift to the left to be a little more specific. Okay. So I always start with my phase shift. That's the first thing I put on the x-axis. So let's maybe put that right here. And maybe make that in a little bit closer. There we go. Now the spacing happens to be by pi over 6. So I'm going to add pi over 6 to this repeatedly. If I add pi over 6 to this, I get 0. And then my next quarter point, if I add another pi over 6, I'll get pi over 6. Okay. If I add another pi over 6 to that, I'll get 2 pi over 3. Okay. If I add another pi over 6 to that, I'll get 3 pi over 6. And 3 pi over 6 is just pi over 2. And then we'll be at 4 pi over 6. Let's see. Oh, you know what? It will be 4 pi over 6, but I'm realizing I have a little typo over here. I'll fix it in a second. So 4 pi over 6 should simplify to 2 pi over 3. This one over here should have been 2 pi over 6, which is pi over 3. There we go. And then next, so this was what, 4 pi over 6, so this will be a 5 pi over 6. All right, and let's remind ourselves what the period was again. It was 2 pi over 3. Okay, so we probably don't have enough here yet for a full period. So I'd say let's add in some more. So then we'll end up with a pi over here. We add another pi over 6, and then a 7 pi over 6. Maybe I'll add a few more on this side. If I take away another pi over 6, I'll get a minus pi over 3. And let's maybe take away one more. And then the next one will be minus pi over 2. There we go. All right, so now let's go back and see what function we're working with. I believe it's cosine. Yeah, cosine. And so you might remember cosine starts at the top of the wave. So the top of the wave for us should be 2 units above the middle. Okay. So 2 units above the middle of the wave is actually up here. You can actually put in, if you prefer, the top of the wave and the bottom of the wave. Some people like to do this. I usually skip it, but I think when you're first learning, it can be really helpful to do it like this. And so I'll go 2 units down too, just so we can see where the bottom of the wave is. There we go. All right. So again, cosine should start at the top of the wave. However, we've had a vertical reflection. So rather than starting at the top of the wave, we're now going to start at the bottom of the wave. Okay. Again, we have this reflection because of that negative right here. Okay. So we're starting at the bottom of the wave. And specifically, this is where we're going to start, is at minus pi over 6. So I'm going to go over here to minus pi over 6, find the bottom of the wave, and we'll put that in. There we go. My next quarter point, if I'm moving to the right, I should now go up to the middle of the wave. And then the next quarter point to the top, and then back down to the middle, and back down to the bottom here, back up to the middle, then to the top, and then the middle, and then the bottom. And let me fill in the rest of these off here to the left. Back up to the middle, and then back up to the top. So let's connect these with a smooth curve that looks like a sine or cosine wave. There we go. All right. And so you can, again, think about this in multiple ways if you're curious whether or not you've sketched 2 full periods. One way we can look at this is we could try to look at maybe how many of those downward facing and upward facing parabolic ish shapes that we have here. So it's what I'm kind of getting at here is here's one down one, here's an up one. So that's one period, and then a down, and then another up. So that's 2 full periods. But you can also think about this if more so thinking about what the parent function for cosine looks like, right? We know it starts at the top of the wave. So like this is what one period of the cosine, what a cosine function usually looks like if we're going up here and looking at that parent function here. Now, the question is, have we made two of these? Yeah, we have. We have another one right here. Okay. So we have over two full periods here. I just want to make sure we're satisfying the directions up here, which say that we should graph at least two full periods. Now, there is another way that you can check, which is you can make sure that you've graphed at least double the period. Okay. So you would want to make sure you've graphed at least 4 pi over 3 units. Okay. And we definitely have here. Okay. So one more of these. Here we're going to attempt to write a cosine equation here. So there's actually an infinite number of cosine functions that we could, um, or there's an infinite number of equations that would give us this picture that we're seeing here. But with cosine, I typically will try to find the peak that's nearest the origin. And so that peak here is right here. And the reason I want to think about that is because this tells me the phase shift. So down here, I'm going to maybe say that the phase shift is pi over 6. And I'm even going to, again, note that C then is pi over 6. Okay. All right, so we have that. Another thing we might be able to figure out here is the period. So the period can be thought about in multiple ways. But one easy way is to just go peak to peak. So my period should just be the difference of pi over 6 and 13 pi over 6. So let's go ahead and fill that one in. So the period here is just going to be equal to that 13 pi over 6 minus pi over 6, which is 12 pi over 6, which is 2 pi. Okay. So cosine without a horizontal stretch or compression will have a period of 2 pi. This tells us that B, the thing that affects our horizontal stretches and compressions, must just be 1. So we have B, we have C, and so we've actually found the harder two first here. Okay. So next is what we could take a look at is maybe what's the amplitude? And you can see from the middle of the wave to the top here, we have 2 units. Okay. So our amplitude is 2. And I should also note, well, A equals 2. That's the more important part here. And then lastly, has there been a vertical shift? Is the middle of the wave, has that been shifted off of the x-axis? And the answer to that is no. There has been no vertical shift here. So D is equal to 0. And so that means we can now write the equation. Y equals A. So A for us is 2. We said we were asked to use a cosine function. Let's see what variable. The variable isn't specified, so I could use x or theta here. It doesn't really matter. Go ahead and use x. So then we have b, which is 1. So I don't even need to write in b. I'm just going to say x. Okay. And then it should be minus c. So it's minus pi over 6. And then there's been, again, no vertical shift, so I don't need to write plus 0. That's unnecessary. So this right here is what we're looking for. All right, and so that there wraps up section 5.3.